www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
I'd like to start out with giving you some motivation for nanoelectronic modeling, this NEMO tool, and give you a background of why this is important and why modeling can be critical. So you probably are well aware of Moore's law. This is a sketch from Gordon Moore's notebook. It's posted on the Intel website. And what he really plotted in 1965 was the relative manufacturing cost per component versus number of components per integrated circuit. And he claimed that this would go down on a log scale. Meaning he was really interested in packing more things into a circuit and in addition reducing the cost. It had nothing to do as such with technology. It was really driven by reducing cost and driving revenue. This is another form of what you might have seen Moore's law in. It has sort of become a self-fulfilling prophecy where as the number of years progress, the number of transistors on a chip is increasing on a logarithmic scale. And we're now at 1 billion transistors on a chip. To put that in perspective, that is making little switches identical, 1 billion at a time on a thing that's as big as your fingernail. That is quite an achievement, a technical achievement, not only to make that happen, but also to make them work together in an appropriate way. That is only possible by design of circuits on computers and design of devices and improvement of devices on circuits. Another way to look at Moore's law is really look at the technical developments in the last few years. And I really like this chart by Robert Chow, who's a fellow of Intel. This is now a chart of 2004, where he has sort of predicted that the following year in 2005 there would be a 65 nanometer node, and it progresses down to ever smaller nodes. And the interesting thing is that in 2009, indeed, they announced their 32 nanometer node. What to take away from here is that these devices are really now no longer really flat, planar transistors, but they're really three-dimensional objects. They almost look like little X-rays of teeth. I mean, they're three-dimensional. There's multiple materials in there. It's quite a complicated structure. Another way to look at Moore's law or side effects of Moore's law is that if you plot the power density in a chip versus a number of years, it's been roughly flat, going up a little bit in the 80s, and then the introduction of the MOSFET again reduced the power requirements. But now we're at the point where it's as hot as a hot plate on your oven. We're approaching power densities in watt per square centimeter of that of a nuclear reactor. Clearly, it's not going to get a whole lot hotter than that because your chip is going to melt away. So there's an issue on heat and being that an unmanageable problem. So another way to now say, well, we need to model these devices is if you really have this schedule that you move forward with over the time of development, you have to realize that the high-end companies that really push the envelope are always a couple of years ahead in terms of their production. And the companies that are lagging a little bit behind pick up the technology a little later. And if you want to be a technology company that leads, you need to be ahead of the curve in order to sell the high volume, high priced chips early on to get more money. So it's really the increased cost of the research and development of the facilities force companies to develop ever faster. And to do that in experiments is really expensive. So if you can do it on a computer and do it virtually, it's less expensive. And it allows you to shorten the process cycle, and it also allows you to reduce the cost in the manufacturing processes. So that brings us to why what you want to do TCAD. What you want to do is ask what-if scenarios rapidly, provide problem diagnosis, provide in-depth understanding of the problems, and decrease the design cycle, and really shortening the time to market. And some of the prerequisites as listed by Bob Dutton, who is sort of considered the father of TCAD, are that modeling and simulation require enormous technical depth and expertise, not only in simulation techniques and tools, but also in the fields of physics and chemistry. So I think this is very important to realize. Even if you run simulation tools, you can't be a code monkey. Okay? You have to really understand what is in these tools and also understand the physics. You also have to understand that these tools are just tools that are coupled well to experimental data. So if you do this all just in vacuum without connecting to experiments, you might be doing a nice Gedanken experiment and a nice theory exercise, but you're not really helping anybody. So theory in isolation of experiment is not really all that powerful. Certainly not in this world of semiconductor devices. And ultimately these tools that are being created by vendors or by universities really need to be closely tied to research and development laboratories. You can't develop software that does this TCAD work in isolation either. So there's a close connection between software development, theory development, and experiment. And only if that is coming together can you have impact with this TCAD development. To give you some perspective of how device simulation really has started and progressed, so in 1964, Gummel introduced a decoupled scheme for the solution of Poisson and the continuity equation. Then Demare introduced the scaling variables that we still use today in '68. And in '69, Scharfetter and Gummel had a seminal paper where they really explained how to discretize the continuity equation, which has been driving a lot of the TCAD development. So it's going quite back far. And what you end up doing is you couple the electronic structure and the lattice dynamics to some transport equations, and they are coupled to electromagnetic fields, and they're coupled to the device simulation. So this is a core element of most device simulation engines, that they have these components. To give you an overview of some of the models that do exist out in the field, there's a semi-classical fluid models, which are basically solving the drift diffusion or hydrodynamic type equations, and there's Atlas and Centaurus or Padre, and they can give you drift velocity and energy density in some of the devices, and they deal with particle density and velocity saturation and mobility modeling. Those are critical elements of what these models deliver. Then the next stage in sophistication is sort of the Boltzmann transport equation, to solve that directly, to really, instead of modeling a fluid, modeling particles. That is accurate in semi-classical limits. It can describe scattering in those limits quite well, and it can even treat ballistic transport in devices reasonably well. And it's typically solved within a Monte Carlo method, so you do statistical sampling of the equation rather than solving it directly. And then the next stage of sophistication is really dealing with quantum effects and worrying about quantum transport. So there's really three phenomena that you have to be aware and include. There's this effect of tunneling that you might have through a gate dielectric. The charge that is sitting against this gate dielectric is not a semi-classical charge, but it's actually a quantum mechanical charge density, so it looks different from a semi-classical density because there's wave functions sitting in this triangular notch. There's also this resonant tunneling diode, which is a completely fundamentally quantum mechanical device that is based on interference effects. And these interference effects are even visible at room temperature. So these are not just pure physicists' devices, but they could be real devices operating at room temperature too. And ways to treat quantum transport have been defined by a couple of people. And I'm going through a few of these. So the Wigner function or the density matrix approaches can deal with correlations in space. They cannot deal with correlations in time. What they can do is treat scattering, but they take a lot of simulation time to run compared to the semi-classical tools. The non-equivalent Green function approach is probably the most fundamental and accurate one, but it's also by many considered the most difficult one to understand and to approach. What's beautiful about it is that scattering is built into this approach very fundamentally. It's not an ad hoc way of patching and scattering, but it's theoretically straightforward to include incoherence and irreversibility. The implementation of this algorithm is rather difficult and time-consuming to compute, and also not simple to implement. So this chart gives you a little bit of an overview that the length scales and the interactions in your devices really determine the most appropriate model. So which model should you use? The drift diffusion type model or hydrodynamic model, Monte Carlo, or the Schrödinger equation approach really depends on the length scale that you want to work in. And what you sort of see is that in older ICs, traditional ICs, the drift diffusion model is still the major workhorse where your transport regime is diffusive and scattering happens often, so there's lots of scattering, and drift diffusion is quite a good way to deal with that. But as you make devices comparable to the electron phonon length, you need to consider other methodologies like this hydrodynamic model, and as you go smaller, compared to the electron-electron interaction lengths, you end up having to do Boltzmann type solutions. And really, we're approaching the limit where either the wavelength of the electrons is comparable or even larger than the device lengths. And that means you really have to consider quantum transport approaches as we deal with nanowires or superlattices and these ballistic transistors. So that gets us back to this chart that I showed earlier. And what I want you to be aware of that the industry really plans 5 to 10 years ahead. So again, when Chao showed this slide in 2004, he had quite a long horizon already. And the really neat thing is, I mean, they are on time. So Intel did put in their schedule a 32 nanometer device node in 2009, and this year they delivered a 32 nanometer node on the market. This is literally 5 years ahead, right? There's proof to that. The bad part is also that beyond 2015, there is no technical viable solution right now that actually continues on this path. I mean, 20 years back, there always has been a viable solution 5 to 10 years down the line. People knew what they were going to strive for. There were difficulties, lithography and materials and gate dielectrics and metal contacts. I mean, there were difficulties, but there were viable solutions out there that were in the research. There are no viable solutions right now that people feel they're going to enable us to get a faster, cheaper chip beyond 2015. So even here on these charts that were created in 2004, all of this material up to 2011 was sort of Intel material. Beyond that, it's really into research like nanowires, carbon nanotubes, and it's not clear what's coming out there. So another way to look at Moore's law is yet another one where instead of just looking at the 2D feature size in the lithography, which was going down on the log scale, really look at discrete atoms and electrons, where we're now in the realm where you have dopant fluctuations and particle noise problem where as you reduce the number of particles, the number of electrons that are sitting on the gate, if their thermal energy is larger than the charging energy of an individual electrons, you're fine. But if you're approaching the regime where the thermal energy is comparable to the charging energy of a few electrons, then adding an electron or taking it off makes a difference. So you have all kinds of noise problems in your device. And another way to look at, well, maybe you can operate into a different regime where actually the charging energy would be much larger than the thermal energy. And if that's the case, you can talk about quantum dots type devices of single electronics. So that's another alternative people are starting to look at, which is, or have been looking at, is single electronic devices. And they have their own problems too. So the other thing I like to highlight in this foil is here that people most of the time look in terms of a 2D feature size in terms of Moore's law. But the layers of these devices are already extremely thin. They're a few atoms thin. So even to do the device modeling in this vertical in the growth direction correctly, you need to do quantum mechanics for many of these devices already. So that's important, and that really motivated a lot of the early NEMO 1D work where we started to look at fast electronic devices like resonant tunneling diodes and lasers and detectors, which are in general built as heterostructures with growth dimensions where you have 5 to 100 angstrom layer thicknesses. So here again are the device trends and challenges. So what I observe here is that there's 3D spatial variations on a nanometer scale. There's potential variations on a nanometer scale because you have gates that you drop charge or potentials over, and you funnel charge through it. There's new channel materials people look at, germanium and 3/5s. And then the questions and challenges are that these devices are highly strained. We know that already, that strain is actually being used to enhance device capabilities. So how do you treat that? How do you treat the quantization? How do you deal with crystal orientations? The number of atoms are countable in this. Does this granularity matter? Does the disorder on these devices matter? And how do you treat all these new materials or the new devices? Or is it actually a new material when you look at that? I mean, you have a composition that you don't find in nature. You're creating a new material in a sense. So it is very conceivable to think about this as being a new material that you need to treat in materials perspectives rather than in device perspectives. So what I'm asserting here to be important is that all of this is operated at high bias and in non-equilibrium. So if you have a quantum mechanical theory that works well in equilibrium, that's fine, but it won't solve you these problems for electrical engineering. You need to do quantum mechanics. I also assert that you need to have an atomic or atomistic representation, that effective mass models really go out the window because they're a continuum representation of matter. And you need to deal with band coupling, non-parabolicity, valley splitting, and you do need to worry about local disorder, strain, and orientation. And all of these elements I'm going to try to highlight in the next few days in these lectures. So I give you a flavor of why this is important and how you might observe these effects. And the way I look at this as a hierarchy of models is as follows. You might have started from macroscopic dimensions. That's how we learn most of our physics. And you think about going down in atomic scale, down to an atomic scale where you start from diffusive into ballistic into quantum transport. And since as electrical engineers we start with this drift diffusion and Boltzmann transport, it really, for a long time, it wasn't clear what is the right formalism to treat this realm. Now what I'd like to drive home here is that if you want to do quantum mechanics, you have to devise a Hamiltonian that describes your system. You can do that quantum mechanically, and most physics courses will teach you about laws of equilibrium, even quantum mechanics. That's fine. And you learn a lot. But it doesn't help you to do devices, because in a real device, you might have scattering, and you can do that in equilibrium too. But what you really have is contacts. You have non-equilibrium. You start to apply a voltage across, and that means carriers are flowing through the structure. And that structure itself is out of equilibrium. That's a fundamentally different property of the material and the device. So you really shuttle an electron through and you add it in the other end, and then you have to reestablish the reservoir potential. And so what the non-equilibrium Green functions really allow you to do is treat that non-equilibrium condition with a full Hamiltonian. That's its real strength. And to treat the contacts. And from there you can actually derive the Boltzmann equation, and from there you can also derive the drift diffusion equation. So it's not that it's sort of an imposed new thing, but you can really fundamentally go back to the theories you like, and it provides you a unified way to look at all kinds of different devices. You can look at silicon nanowires or silicon slabs, you can look at carbon nanotubes, you can look at transport through molecules. The theory that underlies it is the same. The basis set that you represent your devices might be different. But the fundamental theory, the fundamental equations that are being solved are the same. That's a beautiful thing about a unified model. When we worked on NEGF at Texas Instruments, we did explore a variety of theories. So we had, in a sense, the general non-equilibrium statistical mechanics approach and the typical single particle Schrödinger wave function approach that you learn in quantum mechanics classes. And they can be somewhat connected, where you, from the single particle Schrödinger approach, you can start to derive a density matrix or multiple sequential scattering or a stochastic Schrödinger equation to solve that. From the non-equilibrium statistical mechanics, you can try to do a direct evaluation that would be a quantum Monte Carlo simulation, or you can derive the non-equilibrium Green Function Formalism. And in a sense, these two here, the stochastic Schrödinger equation and the quantum Monte Carlo, are related by different sets of averaging approaches. So in a sense, what we had coded up in NEMO as prototypes were the single particle Schrödinger equation, multiple sequential scattering, the stochastic Schrödinger approach, the NEGF approach, and we had played a little bit with a quantum Monte Carlo and density matrix, but not very strongly. So this part gets me to the conclusion of this small lecture, that really the semiconductor industry has fundamental issues and problems. They're really driven by a revenue stream. It must be cheaper and better, so people throw away their old computers. That's the bottom line. That's what they live on. They're not necessarily interested in fundamental understanding semiconductors. They're driven by revenue. The devices are already at the nanometer scale. The wavelength of the electrons are comparable to the device scale. That means the existing tools are fundamentally not suited because they're not quantum mechanics based. I mean, they can be tuned to give you some insight or some scaling capability, but they cannot lead you from one device to the next and be predictive because they are not quantum mechanical. Also, these devices consist of countable number of atoms. It's no longer a huge chunk of device and granularity didn't matter. Now you can count the number of atoms in a layer. So these existing tools are all built on continuum matter theory, right? There is no concept of atoms in there. You can subdivide any domain you want to or discretize in any space you want to. It doesn't matter, right? But that is not reality of discrete atoms. Also, these devices consume too much heat. And then the question is, are there alternative designs? And really, the existing tools cannot handle the quantum mechanics, the atomistic granularity, and the thermal transport in these device domains. So there's real need to build tools for this area. So that's why we worked for many years now on NEMO, and now we're going to build a new NEMO, which is Omen. And the assertions and the agenda is that if we want to have production level industrial semiconductor devices, we need to have look at spatial arrangement in 3D that are no longer planar. We have the dimensions where the atoms are countable. We involve new materials. We need to have a fundamental theory for modeling that is including high bias and carrier interactions. It needs to be including an atomistic basis. And I would claim that theory has been developed. It's NEGF. And you need an implementation of all of that. And it needs to be validated against experimental data. Again, I want to drive home, if you post a theory or a simulation engine, you need to work with experimentalists to really validate it. It must be predictive, because really the goal is to not do that many experiments, right? To cut down the time for development. That means your tool must be able to predict reality, not just after the fact clean up when, yeah, there's a little wiggle on that curve and I can explain it now. And it needs to deliver physical insight, right? The answer can't be, well, the computer said so, right? At the end, you still have to understand your devices and your results. And it must be efficient, because if your computer program takes 93 years to run, it's probably irrelevant for the development of the next generation of computers, right? And I would think that we need to teach these methodologies to the next generation and engineers, and I guess that's why you're sitting in this class. So if you have any questions, I'd gladly take any questions. It's so clear, so convincing. Okay.